My name is Dave Van Vranken, and I'd like to welcome you to OpenCourseware's version of Chemistry 201, Organic Reaction Mechanisms. Over the next 30 lectures or so, I'll be taking you through how we at UC Irvine push arrows in organic reaction mechanisms. And so let's get started. Okay, welcome to Lecture 1 for Organic Reaction Mechanisms 1. Our first lecture is to introduce arrow pushing, and I want to invite you to read in the required textbook for the class. It's by Ian Fleming, Molecular Orbitals and Organic Chemical Reactions. I suggest that you read the preface and then skim Chapter 1. There's important concepts in there that you will use, but you don't need them to have all of those concepts memorized for this first lecture. The other pair of papers that I would recommend for you to read is one by O'Hagan and Lloyd that introduces the history of the curved arrow in organic reaction mechanisms. And you might want to go back and take a look at the original paper in 1922 where arrow pushing mechanisms were first introduced. Let's go ahead and start off by just reminding ourselves of what this course is all about. Okay, so what is Chemistry 201? It's part of a 2-quarter graduate level chemistry sequence at UC Irvine to teach basic organic reaction mechanisms. About 15 years ago, we realized that students were finishing their first quarter of graduate level organic chemistry courses knowing a lot of things, but not being really good at arrow pushing mechanisms. And we decided to correct that by reorganizing the course content. So in the first quarter of organic reaction mechanisms at UC Irvine, we cover arrow pushing mechanisms, molecular orbital theory, structure, bonding, and energetics. And that's what my course is going to be about. We also teach a second quarter course that covers equally important concepts: pericyclic reactions, radical reactions, conformations, stereoelectronics, and mechanistic tools. So let's go ahead and get on with the business of arrow pushing and how we see that fitting into a broader picture of organic chemistry. And I want to start off with a basic question, and that is, what happens when you see a mechanism like this, and you're asked, or a reaction like this, and you're asked to write a mechanism for that reaction? Frequently, you'll draw something on a piece of paper and wonder if what you have drawn is correct, and so you'll go to find answers to what is the mechanism for this reaction. You can look in the backs of books. You can look on the web. You have so many resources available to you. And unfortunately, if you go to those resources and look for what is the mechanism for this reaction, you won't get a clear and consistent answer. This is one of the most important reactions in biology. It's formation of an imine. It's one of an extremely important reaction in organic chemistry in the field of organocatalysis. And if we look at the answer that's present out there, you'll find various different mechanisms. So here's an example of a mechanism that I found. And it starts off by showing that this nitrogen forms a bond with this carbon atom. You can see that bond over here. And then in the next step, you can see a hydrogen atom moves from this nitrogen over here to the oxygen. And then there's the interaction of a proton here. But if I look at some other resource, I won't find exactly the same mechanism. Here's another mechanism that is out there for this reaction, and it starts off showing arrows, and that's always valuable, these curved arrows. This one starts off by showing you that you break a CO double bond, and then an electron pair on nitrogen attacks the carbon atom, and then this proton gets lost, or this hydrogen atom gets lost. It's not the same as the mechanism that I just showed you. The arrows are in different places, the steps in bonding are different. Here's another mechanism. This one doesn't show the pi bond, the double bond breaking. It shows the lone pair on oxygen attacking the positive charge on a proton. And then it shows you that this CO double bond breaks to give the electrons to oxygen and satisfy that positive charge. And then in the next step, it shows you that this oxygen atom is grabbing a hydrogen. This is clearly different from the mechanism that I just showed you. And if you were looking for the right answer that was going to be graded, you'd want everything to look the same. Here's another mechanism. This one is in color, so it must be correct. So here the nitrogen atom is attacking a carbon, and that kicks the electrons from this double bond up to oxygen. And then this negative charge bends over and grabs a hydrogen atom. This is a different mechanism from the one that I just showed you and from the other 3 mechanisms. So why is it that organic chemists can't seem to agree on the reaction mechanisms for this very important reaction? This is a common question that you'll face among a series of common questions. Why can't organic chemists agree? We all agree this reaction is important, even for this simple and fundamental reaction. Worse yet, you might be trying to answer some question on a problem set that you'll be graded on, or on an exam. And you'll wonder, when you try to draw out an answer, why doesn't my mechanism match the answer in the textbook? Is the textbook wrong? Is the answer you just wrote wrong? And more perniciously, if you try to look in the literature, the research literature, and you write out some mechanism, and you'd like to know whether the mechanism you wrote is plausible, is correct, unfortunately, you'll find in many cases that your mechanism doesn't match that printed in the journal article. And the journal article, because it's peer-reviewed, has a level of gravitas that makes you feel like, well, my mechanism must be wrong. Whatever I see printed in the literature or in a journal article must be correct. And the way to resolve all these questions is to reduce it down to a fundamental problem. They're all related in a sense. And that is that organic chemists have never agreed on rules for arrow-pushing mechanisms. Not since 1922, when they were first introduced, organic chemists have never agreed what they were going to use arrows to represent. And so that's the fundamental problem that leads to all of these questions on the part of people who start in the field of organic chemistry. And so we're going to attempt to resolve this problem. So I want to start off by showing you what are the key features of an arrow-pushing mechanism that I expect when somebody says that they're drawing a plausible arrow-pushing mechanism. And the first and most important feature of an arrow-pushing mechanism is that you need to break a reaction, a chemical transformation, into a series of elementary reactions. So I've taken that imine forming mechanism here and I've broken it down into a series of elementary reactions. How do you know that this is a series of elementary reactions? 1, 2, 3, 4, 5, 6. Well, let's go ahead and give a definition to elementary reaction so we're all on the same page. So by definition, an elementary reaction has two properties. An elementary reaction has a single transition state. So if this truly is an elementary reaction step, it has to have one and only one transition state. And it has to match an energy barrier in the reaction coordinate free energy diagram. If I draw out a mechanism that has 6 steps, that correlates with a reaction coordinate energy diagram that has 6 energy barriers on the way to products. So elementary reactions have a single transition state. There's another property of elementary reactions, and that is that they're microscopically reversible. And what that means is that if I say that in this step I'm going to use this lone pair to pull off a hydrogen atom, to pull off a proton from this acid, then if I talk about the reverse reaction, I have to use this A minus to pull the proton back off and go backwards. I can't use a different mechanism or a different type of reaction to do that. It has to involve the same transition state. Now, we're not going to use this microscopic reversibility property so much in this quarter, but it's still an important property of elementary reactions to keep in mind. So what's the second feature of an arrow-pushing mechanism, number 2? The second feature, of course, is to add curved arrows, curly arrows, to your reaction mechanism. So first we need to know how many steps are in the mechanism, and then for each of those elementary reaction steps, we need to add curved arrows to show us which bonds are forming and which bonds are breaking. So how do you decide whether the curved arrows that you've drawn are any good? Whether they represent reactions that are likely to happen or not likely to happen? And I want to try to get you to think about chemical interactions. When two molecules approach each other, when two molecules are in proximity, how do we assess whether that's a good interaction or a bad interaction? So if you think about the factors that influence non-bonding interactions, this is the kind of equation that organic chemists and inorganic chemists and all chemists will tend to use to think about non-bonding interactions. If you want to assess whether the interaction between two entities is good, there's 3 terms in this equation, and they are all distance dependent in some way. So the first term, the first factor that we think about when two molecules interact is governed by this equation, and you'll recognize this as a form of Coulomb's law. You can see there's a distance dependence, so the farther away, the weaker these interactions. And this is the interaction between two charges. And so we frequently use this to think about interactions between charge groups. For example, you might find these types of two functional groups in an enzyme active site where some aspartate carboxylate side chain with a negative charge interacts with some quaternary ammonium ion. or maybe negatively interacts with some sort of sodium ion. These are really informed by this Coulomb's law equation. There's another two terms in this non-bonding interaction equation that are also heavily distance dependent. One of those terms is repulsive, it leads to positive energy, and the other term is negative and it leads to some sort of an attractive force. And these are what we refer to as the van der Waals interaction. These two types of terms tell us why, or help us to explain why and to what extent helium wants to form a liquid. It also tells us why methane wants to be a liquid on the surface of the moon Titan of Saturn, or why methane might want to have some positive interaction of methane. These are good for quantifying these types of interactions. Unfortunately, this equation is not very useful to organic chemists. So organic chemists, and throughout this course and throughout your career, you should think about a different equation to quantify, even in an empirical way, the way molecules interact. So if you're really interested in chemical reactions that form covalent bonds, then we use a different type of equation that has three different terms that are also distance dependent. And so the first term in that equation you'll immediately recognize is this Coulomb's law term that we had in the previous equation. So if we want to think about the interaction of this alkoxide with T-butyl bromide, this is ready to form a covalent bond, and you could use this equation to judge how good the interaction is with this negatively charged oxygen and this carbon atom here with a partial positive charge. And it would explain to you why oxygen doesn't want to attack bromine, because that has a partial negative charge. It would also tell you, because of this term right here, that there are repulsive interactions to consider. So when we draw these out, each of these out, it's easy to see that the negative charge on oxygen might be attracted to this carbon that has a partial positive charge. It's easy to see that as this ethoxide anion gets closer and closer, maybe this carbon atom here might start bumping into these methyl groups. And then finally, if we really want to understand the outcome of this reaction, it turns out that this reaction is going to generate a double bond. It's called an E2 elimination reaction. We have to somehow turn to this third term. This third term tells us why you form covalent bonds. This third term tells us that the oxygen, maybe even if it wants to form a bond to this carbon atom, will instead choose to pull a proton off of this carbon atom and generate a CC double bond. So we have to think about this third term here, and we have to think about what arrow pushing is going to mean to us and how we're going to use it. So let's go ahead and come up with some sort of an agreement. We're going to use arrow pushing to represent something, and we have to decide whether we're going to use arrow pushing to represent charge interactions, whether we're going to use arrow pushing to represent repulsive interactions, or whether we're going to use arrow pushing to represent attractive interactions like this. Now, I think we can all agree that charge is an obvious concept. We reinforce this concept with notions like, oh, opposites attract, or familiarity breeds contempt. I would argue that we don't need to use arrow pushing to represent the interactions of charge. I think this is intuitive, even to non-scientists, this idea of opposites attracting and like charges repelling. And I would say similarly that sterics is also an obvious concept. So these repulsive interactions, if you've ever used a hammer to drive a nail into a board or set a book upon a table, you know that the hammer doesn't fly through the nail even though it's mostly empty space. You know that a book doesn't pass through a table. And these are all concepts that are completely obvious. We don't need arrow pushing to demonstrate those concepts. We need arrow pushing to help us understand the things that are hard to see. And so there I would argue that it's the third term that's not so obvious. And if we look in a little bit more detail at this third term, we can see these abbreviations here. That stands for occupied orbital, interacting with unoccupied orbital. We can see some terms here that reflect the difference in energy of those orbitals. Coefficients on the atoms, overlap of orbitals. This third term is mysterious and may not be familiar to you. And it involves things that we don't see, and that is molecular orbitals. When I drew those molecules for you for ethoxide interacting with T-butyl bromide, nowhere in there did I draw the molecular orbitals. And so